Well, thank you very much. It's a real pleasure to be here. So I gave a sort of broad abstract. I mentioned a lot of things in it, but as I was preparing these lectures, I decided I was going to actually make them a little bit more narrowly focused. And so what I'm aiming for in these lectures is a new technique that Dan Minahan and I have developed for proving finiteness and algebraicity kinds of results. But I'm not going to get to that until the third and fourth lecture. So instead, I'm going to spend the first two lectures giving very, very, very classical background information. And so in particular, since this is aimed at graduate students or maybe people that are not necessarily experts in the subject, my first lecture, I'm going to give an introduction to the mapping class group. And I'm also going to give an introduction to sort of how we think about finiteness properties of the mapping class group and where they come from. So that's what I'm going to do today. Let's see if I can figure out this Blackboard technology. Okay, so that one can go to right there. So I guess I'll try to use this one first. So let's see here. So let me begin. Well, it's supposed to be at the mapping class group, so I should first begin by maybe defining what the mapping class group is. So let sigma G be a genus G surface. So it looks something like this. Here's a genus 2 surface right there, closed oriented. So the mapping group, so mod G, that's the mapping class group. And what is that? Well, what you do is you take the group of orientation preserving diffeomorphisms of sigma G, and you identify two of them if they're homotopic, modulo homotopy. You could replace homotopy there by isotopy. You could replace diffeomorphisms by homeomorphisms. In these low-dimensional settings, none of those distinctions really matter. Those sorts of fine distinctions only start mattering in higher dimensional topology. So in low dimensions, there's many different ways you could set this thing up, and they all give you the same answer. Okay, so this is the subject of this talk right here. And so I should give you some elements of it. Here is one natural, the most naive thing you might do if someone hands you a surface and says, give me some self-map of this surface. Here's one example. Well, so let's say that R from sigma 3 to sigma 3 is, I'm going to call this thing a 2 pi over 3 rotation. What do I mean by that? Well, let's draw a very symmetric surface. I apologize, my handwriting is bad, my drawings are bad. This is supposed to actually have a symmetry, even though it's, the best I can do. And so R just rotates by one click, in that direction. So this right here, so thus R cubed is 1. And so here's a question for you. So why is R a non-trivial element of the mapping class group? You should think about that for a second right there. Why is it not homotopic to the identity? And of course, this is not very hard. There's an obvious thing you can observe. Let's say we take that curve right there. We'll call that gamma. This right here is what R of gamma looks like. Oops. R of gamma is that curve right there. And we observe that, so R of gamma is not homologous to gamma. So R acts non-trivially on H1 of the surface, H1 of sigma 3, which is, of course, that's z to the 6. It's the sort of usual z to the 6 that you're all familiar with, and is not null homotopic. So Okay, the most naive thing you could think about doing worked, right? And it's not an accident. So for finite order elements, they're always going to define non-trivial mapping classes. So this is, in fact, a theorem. This is a theorem of Hurwitz from 92. That's, of course, 1892. That says that, so for G at least 2, all finite order elements of the orientation preserving diffeomorphism group of sigma G act non-trivially on H1 of sigma G. So if you write down any finite order diffeomorphism, any symmetry of a surface like this, it's always going to act non-trivial in homology, and thus will always give you a non-trivial mapping class. And so you can imagine a vast store of finite order mapping classes. There's lots of ways of symmetrically drawing surfaces and then coming up with finite order diffeomorphisms. This is the same paper, by the way, that proves the Riemann-Hurwitz formula, and it's worth reading. So that's, you know, there's various proofs of this now known. I think the most common one is, I think, due to Serre and uses the Lefschetz fixed point theorem. But there's, but this theorem right here is much more classical. So the proof is very readable even today. Yes. No, R of so this right here. No, this gamma right here, that loop around here, that's not no homologous. It's not no homologous. What surface does it bound? Yeah, but the handle's like so gamma is non-separating, and you can see it's non-separating because here's a curve that intersects it once. Yeah, and so therefore that curve right there, it intersects it once. So if you have a curve that's no homologous, you know, it's going to have a non-trivial algebraic intersection pairing with any other curve. Yeah. Okay. Yeah. Yeah. So gamma. Yeah. No. So I chose gamma. If I had drawn gamma to be this curve right here, then this argument won't work. But of course yeah. So are there any other questions? Yeah, so homology is a very powerful tool in this case, and that's sort of the theme of this. It gives us a vast store of these finite order elements of the mapping class group. But of course, not everything in the mapping class group has finite order. So here's another basic example of an element of the mapping class group. So let's say that, unfortunately, I don't know that many letters, so I'm going to use gamma again. So I'll let X be a simple closed curve on sigma G. So then T sub X, that's going to be the Dane twist about X. And what does this do? Well, I'm going to say it in words. You cut twist by 2 pi and reglue. So that's best illustrated by a picture. So let's say that X looks like, to choose what colors are most visible, I think these two should be visible. So let's say that this right here is X. That looks white, unfortunately. I chose poorly. But, so what happens if we cut, twist, and reglue? Well, the surface, of course, well, it's still that, you know, that's not going to, you know, it's hard to see what's going on from that. But if I draw a little transversal curve like that, what does it do? Well, it's just going to go like this. I keep destroying chalk. I need to be gentler. So I was told earlier today that I am one of the most American people that a certain mathematician in this audience had ever met. And so, you know, part of it is that I have sort of hit things too hard, right? So anyway, this is what this Dane twist does. And so these are basic elements. If X does not bound a disk in the surface, if X is a is a non-null homotopic curve, then this will be actually always be an infinite order element of the mapping class group. And in fact, even better, we have the following theorem, which goes Dane. Okay, so I remember that date. I don't remember the date here. I think that's the 20s. And plus, the way I'm going to state this is Humphreys, Stephen Humphreys, in the 70s, says that mod G is generated by the following Dane twists. So let's just draw a surface that's big enough so that we can see them all. Okay, so now I'm going to have, they come sort of prettier if I draw them in a few different colors here. So I'll try this and see what happens. So I need these ones, the loops around the handles, which are none of those bounded disks. Then I also need the other things right here. I need that one, that one. Turns out those are the only two of those I need. And then finally, I need to have this one right there, that one right there, and that one right there. Okay, so I have that finite list of Dane twists right there. So when you say this, I think when someone first sees this theorem, they think, oh, this is sort of what a typical element of the mapping class group looks like. But how do we reconcile this? I have an interesting element of the mapping class group right there. I have these Dane twists. So here's like a puzzle for you, which will illustrate to you how subtle sort of the composition, the mapping class group is, how complicated a group is right. So the rotation as a product of, forget these Dane twists, but of any Dane twists at all. That's not easy to do. And when you start trying to write this, this rotation as a product of Dane twists, you're going to see that you're going to get an extremely long word in various lots and lots of curves all over the surface right there. And you'll quickly realize that, writing an element of the mapping class group as a product of Dane twists is maybe a very complicated way of expressing it. That's probably not how you probably don't want to think about a typical element of the mapping class group as a product of Dane twists. You probably want to think of it sort of how it moves things around the surface. And in fact, it's a theorem that goes back to Thurston, says the typical element of the mapping class group is what's called pseudo-Anasov, which I don't want to talk about that in these talks, but that basically means it completely mixes up the surface. So any curve, it never goes back to itself. It gets twisted everywhere around the surface. If you start iterating that mapping class and hitting a curve with it, then you're going to get things that wind everywhere and everywhere and everywhere. So you should think about a typical element of the mapping class group as mixing up the surface entirely. Okay, so that gives you a taste for how to think about some basic elements of the mapping class group. And so now comes, a question is, so this says that this group is finitely generated, right? That's what I asserted right there. So there's a question, what other finiteness properties does the mapping class group have beyond just simply finite generation like this? And so that's what I want to spend basically the rest of this talk talking about. Is I want to prove essentially that it has every possible finiteness property. I want to explain why that is and why we've known that since the 60s, the 1960s. Though in some sense we didn't know that we knew that since the 1960s. I know Karen's shaking her head. Yeah, that's a provocative statement I just made. So. I'll explain. So what other finiteness properties does the mapping class group have? So I have to say what I mean by finiteness properties in this context. And so here is the strongest possible condition definition. So a group G is of, we'll call, say, type F. So if it has a compact KG1. So that's the nice, by a KG1 for me is always a CW complex. So there's a compact CW complex whose fundamental group is G and whose universal cover is contractible. Okay, a classifying space for G. So this implies many things. This implies first that G is finitely presented. It implies that each homology group of G, by the way, the homology groups of a group, that's simply the homology groups of a KG1. That's all I mean by the homology. When I talk about group homology, I don't mean some sort of esoteric group, thing in homological algebra where you take Tor or something like that. I really mean just the homology of a KG1. That's good. That's a good enough definition for anything I do in these lectures. Each homology group of G is finitely generated. And also, we have that H d of G is equal to 0 for D sufficiently large. Okay, and larger than the dimension of our KG1. Okay, so that's the nicest part. This is as good as a group can be, right? This is a very finite group. Unfortunately, the mapping class group does not possess this property. It's not of type F. So unfortunately, so mod G is not of type F. And here's the reason. So I wrote down, we see up there, the mapping class group has large numbers of torsion elements. Here's a little lemma. So if G has type F, then G is torsion free. And why is that? Proof. So let's assume that G is not torsion free. And let C inside G be a finite cyclic subgroup. Non-trivial, of course, non-trivial finite cyclic subgroup. And so if X is a compact KG1, so we have a cover X tilde, so with pi 1 of X tilde is equal to C. So any subgroup of a group, this is how covering space theory works, right? You have a subgroup of a group you can pass to a cover. And we see then that, so this right here, so X tilde, so is a compact, well, it's not necessarily compact, but is a finite dimensional KC1. But, so if we, but for, for C is equal to Z modulo some, my favorite letter right here, let's say Z mod L. So we have that H D of C doesn't equal 0 for infinitely many D. So this is a familiar thing. So for instance, if I were looking at if C were Z mod 2, right, then the sort of canonical KC1 would be infinite real projective space, right, which has homology, in infinitely many degrees in every odd degree, right? So contradiction. It contradicts the fact that we have a finite dimensional KG1, or not KG. That's a C. You can't tell my handwriting's not very good. Okay. So that contradicts the fact that we have found a KG1 that's finite dimensional, so it only has homology in finitely many degrees. Okay. So yeah. So this is contradiction. So the which contradict. Let me write this in words. Contradicting the fact. Oh, this is a calculation right here. So there's, I gave an example. I don't want to go through the calculation of the homology of a finite cyclic group, but you can construct a KG1 by taking an infinite dimensional Lin space, right, and just calculate the homology of that infinite dimensional Lin space. Yeah. So for FMAD, so e.g. use an infinite dimensional lens space as a KG1 right there. Contradicting that, so the dimension of our KC1 is finite. Okay, any other questions about that? So that's not something that, so it's unfortunate that the mapping class group is not a type F, but we're going to prove something that's almost as good. Okay, so what we will argue, so here is a slightly weaker condition. So is a slightly, so here is an alternate formulation, I should say. How would you, I said a group is of type F if it has a compact KG1. Note if X right here is a compact KG1 with universal cover X tilde, then X tilde is a contractible space. Space here means W complex, so on which G acts properly, co-compactly, properly discontinuously, and freely. Right? That's what it is. That's how you construct it. That's how covering space theory works. So the mapping class group mod G has a weaker property, which is almost as good. So there exists a contractible space Z, which mod G acts co-compactly and properly discontinuously, co-compactly. And it doesn't act, but not freely, with finite stabilizers. Okay, so finite stabilizers, so I'm going to give you, I'm going to explain how to do this in a second. And so what does this mean? So this implies many things. So this implies, so if it acted, and in fact, it's a little bit better than this. In fact, there's a finite-index subgroup of the mapping class group which actually acts freely, but that's not so important for what I'm going to do. But this implies many things. This implies, for instance, that this implies that mod G is finitely presentable. It implies that the each, HD of Z is finitely generated. There's a little spectral sequence argument to show that. But, and letting, oh, not Z, that should be G. So in fact, so we'll say X equals Z mod G. So we have that the rational homology of G is actually equal to the rational homology of X. So, and X here is a compact, well, space. I keep using, Okay, so we found, what I'm asserting here is that there's a compact space which, we can't find a compact KG1 for the mapping class group, but we can find something that sort of is a pretty nice replacement for a compact KG1 that implies the finiteness properties. Of course, it does not imply the homology is 0 for D sufficiently large. That's the one difference. That's the one thing we don't get because it's just not true. So, but this is where I'm aiming. This is when I say the mapping class group has every possible finiteness property. This is the kind of condition I mean. And so where is this going to come from right here? Well, I'm going to give you something that's actually not this Z right there. I will explain something slightly weaker, but you can soup what I'm going to do up to give this statement. I will show something slightly weaker. So there exists a contractible Z with mod G acting on Z with finite stabilizers, and Z modulo the mapping class group is, is homotopy equivalent to a compact space. Okay, that's slightly weaker than what I stated, but that's what I'm going to do, and that's actually good enough. This is actually what's true, and you can soup up what I'm doing to give you this. Okay, so that's where I'm aiming for the rest of today's lecture. Are there any questions about that? So, and it said I'm supposed to be 20 minutes into my talk, and I am 20 minutes into my talk. So my timing, see, my notes have timing right here. That's the important thing. So I'm very jet lagged. I'm not really jet lagged, but it's complicated. Anyway, but I'm very proud of myself that I'm maintaining that discipline. Okay, so before we go on to explaining where this comes from, are there any questions? Yes. Oh yeah. G here is the mapping class group. G is I'm not maintaining that much discipline apparently. So, yes? Yeah. Well, also, I'm getting things about the finite generation of homology. I'm also getting finite presentability. Okay? And this is the sort of conceptual explanation for why the mapping class group is finitely presented. So, this is maybe a piece of ideology. If someone hands you a group and says that it's finitely presented, what a sort of intellectually satisfying argument for that should not involve moving symbols around that page and doing some calculation. It should involve constructing some compact space with that fundamental group. Okay, that's sort of. Whenever I see a claim that a group is finitely presented, I always ask myself, where's the compact space? And most of the time you can find it hiding in the proof, whether it's explicit or not. Yeah. Yes, a compact CW. Well, this is a compact CW complex has finitely many cells. Yes, that's an exercise. You choose yeah. That's right. Exactly. Yeah. Exactly. Yeah. Yeah. Compact CW complexes have finitely many cells. That's right. Yeah. Yes. The mapping class group structure on Q is trivial. There's a statement here. If I could replace Q by a mapping class group representation, which is defined over Q, right? So there's something there too, but I don't want to talk about coefficient systems and stuff. So. Okay. So what is this right here? So where's my eraser? Okay. So what space am I thinking about here? Well, let's fix. Yeah, So any sort of deep property of the mapping class group probably has something to do with either algebraic geometry or hyperbolic geometry. And so that's one of those two, and this is going to involve both. Okay, so let's fix, fix a hyperbolic metric on our surface sigma g. Hyperbolic metric, this is just a Riemannian metric. Metric of constant curvature. -1, constant sectional curvature. Okay, you don't need to know very much about, you don't need to know really any Riemannian geometry to understand this, don't worry. So what this lets us do then, so sigma g is equal to the upper half space, so just the set of complex numbers with imaginary part positive, modulo some gamma, where gamma is a subgroup of I'll say of the isometry group. That's a lambda? I meant lambda. Did I not say lambda? Oh, I was educated in the United States. I don't actually know my Greek letters. You're lucky that I can read. Okay, so where lambda is inside the isometry group of hyperbolic space. That's this, which is PSL 2R. PSL 2R acts on the upper half plane by linear fractional transformations. That's a familiar picture, I think. So right there is a discrete group with lambda isomorphic to the fundamental group, to pi1, which is my notation for the fundamental group of our surface right there. Okay, so I'm writing my surface as the quotient of the upper half plane by a Fuchsian group. Okay? And so that's one of these things. There are many ways to do this. There are many ways to do this, and they're parameterized by what's called, well, depending on how you're choosing to, what you mean by the word parameterization, either Teichmuller space or modular space. But I'm going to start by with Teichmuller space, which I will explain what that is. So, okay, so I want to look at all the ways of finding some lattice inside PSL2R, some discrete subgroup whose fundamental group is pi1. Okay? And so what you do is you take, well, T sub G, that's Teichmuller space. There's many ways of defining it, but here's the way I want to define it. This right here, we're going to take the set of, so it's going to be maps phi from pi1 into PSL 2R. Let me give myself enough space to actually write what I'm going to say. Such that, so phi is injective, and also the image of phi is a discrete subgroup. Okay. And I'm going to quotient out, there's an obvious action of PSL2R in this by conjugation. So I mod out by PSL2R, it's acting by conjugation. The reason I have to do that is there's no sort of canonical base point here, right? And so conjugating is just sort of changing a base point. And so I don't want to fix a base point somewhere. Okay, so I want to think about what kind of space this is right here. I'm parameterizing all the ways of writing our surface as H2 modulo some lattice. And so the first thing I can do, let's think about what kind of space this is. So here's a naive parameter count. Let's think about how many parameters such a representation depends upon. Okay, so the first thing is, well, PSL2R, those are 2x2 matrices. That's like 4 numbers, right? But they have determinant 1. And so it's really a 3-dimensional real Lie group. So PSL2R is a 3D Lie group. And so now pi1, that right there is the very familiar group A1, B1 up through AG, BG, satisfying the usual surface relation. So there's 2G generators, and there's 1 relation, right? And so therefore, what do you have to do? You have to choose to ignoring this thing about injectivity and discreteness and so on. What you have to choose is you have to choose a matrix for each of these 2G generators to go, satisfying that relation, and then you have to quotient out by PSL2R, right? And so the parameters are well, you need 2G times 3. This is, you have to choose. That's a matrix, for each generator. You have to choose 6G matrices, right? But now you can't choose them to be any old matrices, right? If you choose, they have to satisfy a relation. They have to satisfy the surface relation minus 3. This means that we have to satisfying the surface relation, right? So the dimension of the space, naively, obviously, like this is not a rigorous argument. Naively, the space of homomorphisms from pi1 to PSL2R should be 6G minus 3-dimensional because you have to choose 6G matrices, which that's, each matrix gives you 3 degrees of freedom. But then they have to satisfy 1 relation, so you have to lose a degree of freedom, 3 degrees of freedom to 3. That, and so then minus 3, that right there is conjugate by PSL2R to mod out by conjugation. So the parameters that you need to parameterize Teichmuller space naively are 6G minus 6. Okay, naive. As I said, very naively. That's not an argument. It's just sort of an intuitive reason why that number comes up. And in fact, there's a theorem. There's a theorem which, I'm going to say this goes back. This is like Fenchel and Nielsen. Says that something even better is true. Teichmuller space as a space is actually homomorphic to R to the 6G minus 6. Okay, so that parameter count, actually there are, in fact, 6G minus 6 freely chosen parameters. Let me tell you what those parameters are. So what are these parameters? So let's fix what's called a Pants decomposition. What do I mean by that? Id est. See, I was educated in America, but I can use gratuitous Latin. So a 3G minus 3 loops cutting sigma 3 into 3-holed spheres. A pair of pants, of course, is it's like a sphere with 3 holes. There's like a hole here, and there's 2 holes down at the bottom, right? Here's a picture of that, of one of those. I'll do it for, say, a genus 3 surface. Well, how would I cut that into some pairs of pants? One thing I could do that. I could do that. I could do that. I could do that. And then let's say I did, so that's 1, 2, 3, 4, 5, 6. 3G minus 3 in that case is 6. There's one of them right there. There's of course many. There's choices you can make. There's many choices here. The reason you get 3G minus 3 is because that's just a little Euler characteristic argument, right? You have to glue. You can reassemble these pairs of pants into the surface by gluing them back up, and you have to get the right Euler characteristic. Okay, and so then the parameters. Well, what Fenchel and Nielsen showed was that the parameters, what kinds of things, if you have a point in Teichmuller space, if you have a hyperbolic metric, you have such a representation, you can measure the length of any curve, right? You take a curve, that's an element of pi 1, that gives you have a free homotopy class, your modding up by conjugation. You can take the length of the geodesic representative, right? So you can so in Teichmuller space, so in TG, you can measure the length of a geodesic representing any given simple closed curve. That's the sort of thing you can do. There's a unique geodesic, because it's negatively curved. And so this gives us, what Fenchel-Nielsen shows is that, in fact, the coordinates for TG are, so first we're going to have positive numbers, 3G minus 3. These are the lengths of the 3G minus 3 Pants curves. Right? So we have 3G minus 3 numbers right there, right? But then we also have to know how they're reassembled, right? And so plus r to the 3G minus 3, these are the twist parameters. So, measuring how they're glued together. Okay, so certainly, these numbers here, they're clearly, it's sort of clear what they mean, And so what they really showed was that if you have a hyperbolic metric on a pair of pants on a 3-holed sphere with geodesic boundary, then you have 3 numbers, the lengths of the 3 boundary curves, and in fact, it's completely determined by those 3 numbers, and anything can occur. So the set of hyperbolic metrics on a pair of pants is just given by 3 positive numbers, And then when you glue them, well, you have a choice, and you can rotate them, right? And you might think, that should give me a circle parameter, not a real number parameter. But if you rotate it all the way around, you come back to something that's isometric to it, but the representation is different. There's a twist. There's a Dane twist happening in that representation right there. Okay, so that's the parameter count. That's why this is r to the 6G minus 6. You can find a proof of this in the primer on mapping class groups by Farb and Margalit, which is the sort of textbook I recommend for this. If you don't understand this right here, don't worry. You don't actually need to know it to follow the rest of these talks. But anyway, so we have this right here. Now, the mapping class group should act, right? Now, how does the mapping class group act? Well, So the mapping class group, so it almost, so acts on the fundamental group. The only problem is there's no fixed base point, right? So the action is only, so the action is well defined up to conjugation due to base point issues. You often say that it has an outer action on pi 1. It's an action is a homomorphism to automorphisms modulo inner automorphisms modulo conjugation. And yes? Yeah. Well, the thing that's so you could quotient out. So PSL is a normal subgroup, so I couldn't quotient out by PGLR, but I'm just going to conjugate by PSL. Doesn't really matter, yeah. It shouldn't matter because of projective space, because I'm killing off the center right there. Like that surely shouldn't affect anything. So. Like if I were being very careful and thinking about stacks and stuff, then that would matter. So, but I'm definitely not. So, in any case, so this action is well defined to conjugation, but I'm quotienting out by conjugation. In fact, that's very important right there, right? Because I'm quotienting out by PSL2. So since in TG you quotient by conjugation, so you get an honest to goodness action of the mapping class group on Teichmuller space. Just it's acting on, these are representations. By the way, so there's a larger representation variety. If you throw away the fact that these are injective maps with discrete image, there's a larger representation variety. It turns out that this is actually a connected component of that representation variety. So anyway, so we get an actual action there. And so this action, Teichmuller space is a contractible space. The mapping class group is acting on it. So the stabilizers, this is the action is properly discontinuous, but not free. So, since the stabilizers of points are isometry groups of hyperbolic surfaces. So, if you have the isometry group of a hyperbolic surface, it's always a finite group. Okay, that's basically negative. That's a consequence of negative curvature. So if you have the isometry group of any compact, if you have the isometry group of any compact Riemannian manifold, it's going to be a compact Lie group. Okay, but because of negative curvature, it's actually a discrete Lie group, a compact discrete Lie group. So it's actually a finite group. Okay, so thus, we've gotten most of the way here. Going back to what I said before. So thus, let's so I'll call this thing MG. That right there is Teichmuller space modulo the mapping class group. So this right here is also called, this is the moduli space. Moduli space, there are many moduli spaces in mathematics, but somehow this is the moduli space for history. It was the first one that was seriously studied. So it's the moduli space, in this case, the way I defined it, of hyperbolic metrics. Okay, moduli just means parameter. It's like the parameter space of hyperbolic metrics, where because I'm quotienting out by the mapping class group, I'm forgetting somehow a marking by the fundamental group. I'm forgetting how how I'm identifying my hyperbolic surface with my reference surface. Okay, so this right here, so this is a, it's almost a manifold. So this right here, so we thus have that, at least, the homology of the mapping class group, as I said before, because it's acting, properly discontinuously and almost freely. It's acting with finite stabilizers. It's the same thing as the rational homology of Mg, I cannot yet deduce that the mapping class group is finally presented, because the problem is, or that these are finite dimensional, so the problem is that Mg is not compact. And you already can see that. I said I'm choosing a hyperbolic metric on a surface, right? And I said I can make these curves to have any length I want. So I can take one of these curves and make it shorter and shorter and shorter and shorter and shorter, degenerating to something that's not a surface. It sort of pinches it to a point, and that's like moving out, like moving off the edge of the universe, off the edge of the Teichmuller space into some boundary at infinity, right? So therefore, this is definitely not a compact space. Okay, so this is not compact, but nonetheless, it has finiteness properties. And so what I want to explain now is why this was known since the 60s, that the moduli space of curves has finiteness properties. And so here is an amazing fact. To my mind, this is the most amazing fact in mathematics. Okay, like I can't think of something that blows me away more than this. And I really mean that, as I said, I'm very American, so everything is amazing, right? But in this case, this is a unique point. Like I've said, this is the most amazing thing in mathematics in many lectures over the past 15 years. I really do believe this one right here is the following are the same. So we have a bijection. So in the first thing, we have hyperbolic metrics on sigma g. Those are the same thing as Riemann surface structures on sigma g. Let me say why that is right here. What's going on here? So a Riemann surface structure, this is the structure of being a one-dimensional complex manifold. And so that's just because, uniformization says the universal cover. Oh, I should have said G at least 2 at some point in this talk. When I said hyperbolic metrics, someone should have objected. Those don't exist on spheres or tori, but they do exist on once the genus is at least 2. Says the universal cover of sigma g is biholomorphic to the upper half space, right? That is one statement to the uniformization theorem in the hyperbolic setting. Uniformization says that if you have any Riemann surface, the universal cover is either a sphere, the complex plane, or the upper half plane. But because the genus is at least 2, it has to be the upper half plane. And so the amazing fact is that so therefore it's the same. So i.e., so sigma g is the upper half space modulo a discrete group of the biholomorphic self-maps of H2, right? So that's a something that looks a lot like what we said in Teichmuller space, right? So the biholomorphic maps of H2, that right there is equal to the orientation preserving isometry group of H2. These are both PSL to R. This is an accidental isometry, right? This is one of those facts that need not be true but is. But because of this, if I have a hyperbolic metric, I have a discrete, I've written sigma g as a quotient of the upper half plane by a lattice in isometry, orientation preserving isometries of H2. And that's the same thing as a lattice in the biholomorphism groups. I get a Riemann surface structure, and conversely. Okay, so those are the same thing. But then something that's almost even more amazing is that this is the same thing as algebraic curve structures. So as curve structures. on sigma g. So algebraic curve in this case means you take, you take a one-dimensional smooth projective variety inside some projective, inside projective space, some projective space that is diffeomorphic to our surface, right? That's what I'm on. So I'm writing my surface as the vanishing loci of a bunch of polynomials in projective space. Okay, and these are the same thing. So there is a forgetful map here. If you have an algebraic curve structure, you've written as vanishing loci and polynomials in projective space. Just remember the Riemann surface structure, but the other direction quite. Okay, it follows from Riemann rock. So it follows from the sort of holomorphic version of Riemann rock. But it's quite a deep result. So these are some very deep and non-obvious identifications. But now here is a sort of a very cool fact. So this is a cool fact, which has maybe been borne out by experience, is that moduli spaces varieties. Algebraic varieties come in moduli. You can vary, if you have a bunch of polynomials vanishing in projective space, you can vary the coefficients, right? So you can deform algebraic varieties. And so here we're deforming curves, but you could deform any sort of algebraic variety, right? You can look at their spaces of parameters are usually themselves varieties. Okay. That's a fact that's been borne out by experience. And in fact, we have the following theorem. This was proven by Walter Bailey in, I wrote down that date, 1960. That this one right here is a quasi-projective variety. Let me say what that means. That is, so there exists, so a projective variety so mg bar, probably very singular. There's many, and there's many choices. This is not a canonical object. Bailey constructed one, but there's many other ones that are now known. Projective just means compact, such that mg is an open subset. In the Zariski topology. So we're taking it, we're saying the mg is not compact, but it has this sort of compact closure. Okay, and what I claim is that this right here implies all these finiteness properties. Okay, and so what do I mean by that? What I mean by that, and by the way, I will never talk about algebraic geometry in my next 3 lectures, but I wanted to explain why, you can know without having to know any, calculate in a sort of abstract way, we can know all these finiteness properties for the mapping class group. So here's a basic fact. So, okay, so this is supposed to be a topology lecture. How do you know that compact manifolds have finally presented fundamental groups and finally generated homology groups? Well, we know that compact manifolds, smooth, can be triangulated, right? Smooth. So they're homomorphic to finite simplicial complexes, right? That's the most finite kind of thing in the world, right? So the same is true for projective. That means compact varieties. Okay, there's triangulation results. They're not that hard to prove for projective varieties over the complex numbers. I don't even know what other fields. That's the only field I know. Okay. So any projective variety also has a finally presented fundamental group and finally generated homology groups. Unfortunately, mg is not projective, so that doesn't give us something. But you note that so let's let mg, I forgot to word my word. I'm gonna call this the boundary of mg equal mg bar minus mg. This is also projective. So we can triangulate. So mg bar such that this boundary of mg bar is a subcomplex. And what does that imply? This will be the last sentence of my talk. So this implies that mg itself, this right here is mg bar minus the boundary at infinity of mg bar. This right here is equal to, this is a finite simplicial complex minus a subcomplex. Okay? That's the next best thing to a compact space, right? You know, if we take a finite simplicial complex, you remove a subcomplex, you know, it's no longer a simplicial complex, right? Like for instance, if you take a triangle, the three vertices, that's not a simplicial complex anymore, right? But it's homotopy equivalent to a finite simplicial complex. So this right here, so hence we have that, you know, the homology of mg are all finitely generated, and the mapping class group is finitely presented. The mapping class group is almost the fundamental group of mg. That was, remember, mg is Teichmüller space modulo the mapping class group, and that's, you know, if I allowed myself to work in the category of stacks, I could literally say that it is the fundamental group of this very finite object, but that's not quite true. But it's, you know, it's enough that it's very easy to derive the mapping class group is finally presented from that statement. And so the upshot is that because of algebraic geometry, we know the mapping class group has every possible finiteness property we might hope it could have. And that's where I want to stop today. Thank you.